Hello, this is lecture 2 for UCSB course ECE 257A entitled Fault-Tolerant Computing, Dependable Computing. This lecture deals with chapter 2 in my textbook, Dependable Computing, a Multi-Level Approach, which is available online in draft form. Is being developed at this point, not yet published. The title of the chapter is Dependability Attributes. Basically, we are concerned in this chapter with quantifying dependability. How do we measure dependability? What does it mean if we say one system is more dependable than another one? In what sense is it more dependable? Some cartoons for your enjoyment. You can look at them later. So we are now in chapter 2, part 1 of the textbook. So aspects of dependability or attributes that we use to measure and compare dependability are various. Some of them are listed here. For example, reliability is one of the better known aspects. Availability is another well-known aspect. Testability, safety, security, performability. It's unlikely that you have heard this term before. I will define it before the end of the lecture. Integrity, maintainability, and so on. Now, the terms that you see inside this yellow blob have the common feature that they all end in letters IL, ITY, ility. And for this reason, sometimes they're referred to as the ilities. So the ilities are features or attributes that are described by words that end in ility. So serviceability, reliability, availability, they're examples of ilities. The other terms are also important, but they don't end in ility, so they're not included inside this blob. So we will define most of these terms in this lecture. I just wanted to put all of them on one slide so that you know there are many different terms and concepts that we use to define and compare dependability. First, a review of some key concepts from probability theory. As I mentioned before in lecture 1, we do make use of probability. So if you have not taken a probability course recently, it may be a good idea to brush up on your knowledge of probability by reviewing basic probability textbook. You don't need to review the entire textbook, as the concepts that we need are generally found in the first few chapters, maybe 4 or 5 chapters of any probability textbook. So I'll review some of the concepts here, but not all of them. First, we have something called probability density function, f of t, small f of t. That's the probability that some random variable x is in the range t and t plus dt. So random variable is basically a number, random number. It's in the range t and t plus dt divided by dt. A cumulative distribution function is basically the integral of that density function from 0 to t. So the name cumulative comes from the fact that we accumulate this density over the range 0t and call it cumulative distribution function. Now these two concepts can be illustrated by a simple example. Suppose I observe 20 identical systems until they fail. So I basically measure their lifetimes. And this lifetime is measured in some unit. Doesn't matter what the unit is. Let's view these as individuals, and then we observe their lifetimes, how many years they live. And those dots, heavy dots, are basically the point at which the persons died or the system failed. So there's some distribution. You see that one of those individuals died very early, as a baby or infant, and the rightmost one died after 48 years in this particular population. So that's the longest living person or system. And if I plot the number of systems that failed, or the number of people who died up to a certain point, I get that CDF curve, cumulative distribution function. It starts at 0, nobody has died at that point, and then eventually gets to 1, 100%. All the systems failed or all the people died. And the shape of this curve basically indicates the distribution. In this case, for example, you see that the slope of the curve is highest near the middle. So that means, there's a large density of system failures or deaths in that middle range. The derivative of the cumulative distribution function is the probability density function shown in the second curve. And here you see that the density of failures or density of deaths is largest near the middle. Okay, expected value of a random variable x is defined as the integral minus infinity to plus infinity x times f of x. Oops. So the density function times the value x. So we basically multiply the density by the value x to find the expected value of x, and we integrate over the entire range. The discrete version of this formula in discrete distributions, always the integrals are replaced by summations. So xk is one of possible values, discrete values that the random variable can assume. Probability of that discrete value multiplied by that value summed over all possible k indices, it's the expected value. Variance of x is basically the expected value of as the integral from minus infinity to plus infinity, x minus expected value of x squared times f of x times dx. So basically this is the expected value of this term. The expected value of the square of the difference between x and its expected value integrated over the entire range, or the discrete version again is summation rather than integral. And covariance of two random variables x and y is the expected value of x minus ex times y minus ey, and this can be proven to be expected value of x times y minus expected value of x times expected value of y. These are some basic probability notions on this slide. These are some probability distributions, some simple ones that we may encounter, starting with the uniform distribution. In the uniform distribution, the density function is constant over some interval, the range. This is the possible range of values. And then the cumulative distribution function is basically linear up to the end of that range, and then it's horizontal after that. Exponential, the PDF is exponentially declining. The CDF, cumulative distribution function, has this shape. Normal distribution, the PDF has the bell curve shape. And the CDF, cumulative distribution function, has this shape. And the discrete version of the normal distribution is known as the binomial distribution. So it's basically the same thing, except it has discrete set of values. And the CDF is basically the discrete version of this curve. So these are some common distributions that we encounter. The next notion that I want to discuss is this concept of layers of safeguard. There are some misconceptions about these layers of safeguards. That's why I discussed this in some detail. Now imagine that you want to make a bulletproof vest using some type of sturdy fabric in multiple layers. That fabric, if it's perfect, maybe it can stop a bullet of a certain kind, but the fabric has imperfections, such as the holes that you see in this diagram. So these are sort of cheese slices with holes representing that fabric. And those holes are basically imperfections in the fabric that could allow a bullet to go through. Where there are no holes, the fabric, of course, this does not have to be a cloth fabric. It can be sort of chained metal, sheet of metal made of chains. So some parts of this fabric are imperfect, so they let the bullet through. If you put 4 layers of this fabric, then it's unlikely that all these holes will be lined up as shown in this diagram, and a bullet comes and goes through all of those lined up holes and gets to the other side, killing the person. If these holes are random, then it's extremely unlikely for them to line up the way shown in this diagram. So this is sometimes modeled or analyzed in the following way. Suppose we say that each of these sheets has a 1% probability of not stopping a bullet. Okay, now if these holes, locations of these holes are completely random, and therefore these sheets are statistically independent from each other, then the probability that the 4 layers will not stop the bullet will be 1% times 1% times 1% times 1%, independent random variables. You simply multiply the probabilities together. It will be 10 to the minus 8. So it's extremely unlikely, probability 10 to the minus 8, that the bullet will go through and will kill the person. But this assumption of independence is a big assumption. How can we be sure that that's a valid assumption? In fact, in many practical cases, when you have problems in multiple subsystems, those problems may not be statistically independent. There are what we call common cause failures, common cause problems that may lead to multiple failures simultaneously. So such failures are no longer statistically independent, but they are actually dependent. So for example, if these are four subsystems that we are trying to analyze, but they're all connected to the same power supply, and that power supply fails, then all four subsystems will fail to do their job, their function. So they are not statistically independent. If we want them to be independent or more independent, then we have to provide independent power sources to these four subsystems to make it nearly impossible or less likely for them to fail at the same time. So these common cause failures, sometimes referred to as a single point of failure. So a system that has a single point of failure is susceptible to failure when just one thing can go wrong. Okay, we aim to remove these single points of failures or causes of dependent multiple failures. And if we can manage to do that, then this assumption of independence, multiplying probabilities by each other, will be valid and we can use it. So this is really one of the major sources of errors in modeling dependable systems, assuming independence where independence actually does not exist. So this example is intended to bring this to your attention. Whenever you assume independence, you better work hard and try to verify that assumption. Make sure that it holds so that your results are valid. So a very good example at the bottom of this slide is this situation. It's an old one from 1986. Before the internet, there was something called ARPANET, a precursor to the internet. And this ARPANET connected various centers to each other, and people could send files and emails and stuff like that to each other. So two major hubs of this network were Boston and New York, and therefore the designers of the network decided to have 7 channels, 7 dedicated lines between New York City and Boston, so that traffic can flow smoothly between those 2 points. These 7 channels, ARPA basically leased these channels from different companies that offered connections, digital connections, and they sort of assume that these will be independent. In other words, it will be extremely unlikely for all 7 channels to suddenly become unavailable, and therefore at least critical traffic between the 2 cities could flow uninterrupted even if several of the channels failed. Of course, the common case was that all 7 or 6 of the 7 channels were working and traffic flow was smooth, even if multiple channels failed. This is similar to the example in the figure. So if we say each of these 7 channels has probability 10 to the minus 2 of not being available, 0.1% or 0.01, then if they are truly independent, 10 to the minus 2 to the power 7 will be 10 to the minus 14, which is an extremely small probability that all 7 channels become unavailable. However, unbeknownst to the designers of this network, those 7 supposedly independent dedicated channels all happen to go through the same physical cable. So these different companies actually had leased their connections. They didn't own their own cables between the 2 cities. They had leased their connections from companies that did offer these connections. And it so happened that all 7 channels went through the same physical cable between the 2 cities. So when a construction company operating a backhoe accidentally cut that cable, all 7 channels became unavailable and traffic flow ceased between the 2 cities. Okay, a very good example that this assumption of independence you have to really examine carefully before you use it in your analysis. So that 10 to the minus 14 probability, which is extremely small, was actually not that small in practice because of these dependent failures. Okay, so let's start looking at all these different measures of dependability. The best known and perhaps the most important measure is reliability. Reliability is the probability that the system remains in operational state through some interval 0 to t, and it's applied to systems that have 2 states, up and down. So the system starts in the up state, operational state, and at some point it may fail. That's a probabilistic process. Sometimes it fails quickly, sometimes it fails after a long time, and it goes to the down state, it becomes unavailable. And this is known as a non-repairable system. In other words, once the system fails, goes to the down state, it's finished. You can't do anything about it. You can't repair it. Later we will see repairable systems. Okay, so how do we model the system? Here is basically an equation. Reliability is the probability that the system remains in the good state through the interval 0t. So reliability for the interval t plus dt, a slightly longer interval than this t. So the system survives to the end of this time period t plus dt. If it has survived up to time t, which is the definition of reliability to time t, and then it does not fail in the small time interval dt. It doesn't fail, basically 1 minus the probability that it fails. Okay, so it survives up to time t and it doesn't fail in the interval, short interval dt. Doesn't fail is 1 minus the probability that it fails. And the probability that it fails, we basically say it's proportional to both the width of that interval. The longer that interval, the more likely it is for the system to fail in that interval. So it's linearly proportional to dt. And it's also proportional to something called the hazard function. Hazard function is basically the rate of the failure. So for example, the hazard function z is a function of t. So for example, as a system gets older, the failure rate may increase. So z of t can be an increasing function of t. In the simplest case, z of t is a constant, which we call the constant failure rate of the system. And this actually is true for electronic systems because electronic systems generally do not age. So if a system is functional at time 0, it will remain functional, and then with some constant rate it fails. So we don't have wear out in electronics. And in fact, most electronic systems become obsolete before they become too old to function correctly as a result of aging. So for electronic systems, digital systems, this assumption of a constant failure rate, lambda, is not unreasonable. So r of t plus dt is r of t 1 minus lambda t. So I can say r of t plus dt minus r of t, take that to the other side, and divide by dt, so that's the derivative of r of t, is equal to r of t times lambda. Okay, this is a simple differential equation whose solution is r of t equal to e to the minus lambda t. Remember, we used this exponential reliability equation in the first lecture. Here is its justification. The reliability of a system having failure rate, constant failure rate lambda, operating for a time period t, is given by this equation. Of course, in the equation that we saw before, there was this factor n here in the exponent, n lambda t. That's because there we had n components, and lambda was per component failure rate. So n lambda that we had there is actually this lambda, which is the overall system failure rate. Okay, so this is known as the exponential reliability law. And we have something called mean time to failure. Because failure occurs at random, we may be interested to see on average how long does it take the system to fail. That's measured by this numerical metric, mean time to failure. And that's defined as the integral from time 0 to infinity, t times f of t dt. And it's provable. I won't prove it here. I'll leave it up to you if you're interested. It's the integral of the reliability of the system over time 0 to infinity. So this is the area under the reliability curve. The area under the reliability curve is the mean time to failure. Okay, so for example, for this exponential reliability function, mean time to failure is 1 over lambda, which makes sense because if I say this system has a lambda of 10 to the minus 4, meaning there is on average 10 to the minus 4 failures per unit time, that means that the mean time to failure will be 10 to the 4, the inverse of that. So for exponential reliability law, mean time to failure is easily obtained. It's just the inverse of lambda. So these are some distributions. Exponential, I already mentioned. The hazard function is a constant. Reliability equation is e to the minus lambda t. Mean time to failure is 1 over lambda. And some of these distributions have discrete versions. So the exponential distribution, the discrete version is the geometric distribution. So reliability over k time units, discrete time units, is reliability over 1 time units to the power k. Rayleigh distribution has this hazard function. The reliability equation is e to the minus lambda t squared. Okay, the mean time to failure can be obtained to be 1 over lambda times square root of p over 2. This is not, intuitively obvious why that's the case, but it can be computed by applying the formula for MTTF to this particular distribution. Then we have Weibull distribution, which the hazard function is given here, and reliability equation is e to the minus lambda t, a quantity to the power alpha. So basically, this is a special case of Weibull. Rayleigh is a special case of Weibull for alpha equal to 2. Okay, an exponential is a special case of Weibull for alpha equal to 1. And this is the mean time to failure for Weibull distribution. And that is 1 over lambda times, this is the gamma function. And there's also discrete Weibull corresponding to that. A bit more detail about these distributions are provided in the textbook. I don't go over all the details in the slides. It's much harder to describe these verbally than to read about them in the textbook. We also have gamma distribution. Oh, we have Erlang distribution is general exponential, gamma distribution, and normal distribution. The discrete version of normal is called the binomial distribution, which I referred to earlier. So these are some well-known distributions that you should be familiar with, although we really don't use any of these other than exponential and sometimes Rayleigh and on very few occasions Weibull. So that's why I describe those with a little bit more detail. So this is an example where Weibull distribution comes into play. It's an experiment performed with paper clips, the old style paper clips made of metal wires. So you take a paper clip and you sort of open up and make it into this shape, and then repeatedly straighten this part to look like this and bend it back. It's intuitively obvious that after a few times that you bend and straighten this part, the paper clip will break at this point. And if you put maybe 100 people to work doing this on different paper clips, the number of cycles, the number of times that they straighten and bend the paper clip before it breaks will show a distribution such as this one. So here we see there was a paper clip that broke after, let's say, about 12 times, another one after about 14 times, but there were some paper clips that lasted for maybe 80, 90 cycles, okay? And this distribution is a Weibull distribution with alpha equal to 2.6. So the special cases of Weibull, alpha equal 1, that's the exponential, constant hazard rate. Alpha less than 1, this is when the failure rate actually decreases time. It's known as infant mortality. In analogy with infants, occasionally dying right after birth, but then if they survive the first few days of life, then it's much less likely for them to die as small children. Alpha between 1 and 4 is what corresponds to rising hazard rate, for example, due to fatigue, aging, corrosion, and so on. Alpha greater than 4 is a very rapidly rising hazard rate, where you have rapid wear out due to some unusual conditions. So this is the nice thing about Weibull, because it can model different things by playing with this parameter alpha. In this example, you notice that the data fits well with the Weibull distribution, having alpha equal to 2.6. Of course, it's not a perfect fit. The fit isn't perfect in this part and in the latter part, but for the most part, it's a good fit. By the way, this is a log-log scale plot. It's not a linear plot, so that's why the straight line is really an exponential function. Okay, when we compare reliabilities, we encounter an interesting problem that we need to resolve. So here I've shown on this chart the reliability curves for two hypothetical systems, System 1 has this reliability curve, R1T. System 2 has this reliability curve, R2T. Okay, you notice that the shapes are different. The system 2 is highly reliable in the beginning, but then at some point the reliability drops and goes close to zero quickly after that. System 1 reliability drops, so it's not very reliable anywhere, but then at some point it becomes more reliable than that system 2. Mean time to failure for system 1 happens to be larger than mean time to failure for system 2. Remember, mean time to failure was the area under the reliability curve. So this curve has a smaller area underneath it than this curve, because this curve extends further to the right with non-zero values, whereas this one goes quickly to zero. So the area is really just the part that you see in this diagram. So this is one of the cautions that one has to be aware of. Mean time to failure is a helpful figure to have, but it can be misleading, because this system that is not very reliable, even at the very beginning, exhibits a large mean time to failure, larger mean time to failure than this system, which is highly reliable. Now, if we use this highly reliable system up to this point, up to this time Tm, then reliability is pretty high throughout that period. So the fact that mean time to failure is small really doesn't matter if we don't use the system beyond this point. Okay, so we tend to use computer systems, or any system for that matter, only in the parts of this curve where reliability is high. Okay, so this system, we probably use it for very short periods of time in this region, where reliability is close to 1, but not beyond that. Okay, so how do we compare reliabilities? Well, we take a particular mission time, Tm. That's basically the time the system is going to operate. And notice that reliability is this value for system 2, and it is this value for system 1. And this difference, reliability difference, is a measure of how much more reliable system 2 is compared to system 1. The reliability ratio, reliability gain of our system 2 over system 1 is the ratio of these two numbers. Now, the problem with reliability difference and reliability gain is that systems that we compare often have very close reliabilities. The difference is not as significant as you see on this diagram. And therefore, R2 minus R1 is a very small number, pretty close to zero. And R2 over R1 is a number that is pretty close to 1. So it really doesn't provide sufficient, it doesn't have sufficient distinguishing power, because one of them is almost always close to 0, and the other one is almost always close to 1. So we come up with other ways of comparing reliabilities. For example, reliability improvement factor is the ratio of unreliabilities. Okay, so if the reliability of one system is 0.9 and the other one is 0.99, this difference is 0.09, it's a fairly small number, and this ratio will be 1.1, whereas the ratio of unreliabilities is 10. So this provides better distinction between systems. So the unreliability, ratio of unreliabilities, is what we compute rather than the ratio of reliabilities, which are pretty close to each other. So that's one measure. Reliability Improvement Index has been defined as the ratio of the logs of reliability. Okay? And mission time extension basically says if we have a certain reliability goal, RG, reliability goal, this green line, then system one provides this much time. We can operate it for this much time before reliability drops below the acceptable level. System 2, we can use it for this period before its reliability drops below that agreed upon level RG. The ratio of these two mission times, well, the difference will be mission time extension. How much longer can this system operate compared with this one? And the ratio of the two mission times is called the mission time improvement factor. So it seems in this diagram that this system can operate 4 times as long as this system for the same reliability level. Okay, a few years ago, I published this paper in IEEE Computer Magazine where I sort of brought to the attention of the journal's readers that there's an analog to Amdahl's law for reliability. You probably know what Amdahl's law is. It's basically something to do with performance improvement in systems. And it says that if you have an application, a program running, and you take an aspect of that application and improve it by a certain factor, the overall improvement in performance will not be as large. So for example, if you have an application that does both floating point arithmetic and fixed point arithmetic, and then you redesign your floating point unit to become twice as fast for floating point operations, depending on the fraction of operations that were floating point versus fixed point. So let's say they were equal. Half of the operations were floating point, half were fixed point. Okay, so the running time was 0.5 units for fixed point and 0.5 units for floating point. Now you make your floating point unit twice as fast, so that 0.5 becomes 0.25, and therefore running time becomes 0.75. So you improve the floating point performance by a factor of 2, whereas the overall performance went from 1, overall latency of the computations went from 1.75. It's a much less pronounced improvement. So the same thing is true with reliability. If you have a system that has, let's say, 2 parts, one has failure rate phi, one part, and the other part has the remaining failure rate. So the overall failure rate is lambda. One part has failure rate phi, the other part has failure rate lambda minus phi. And suppose you take this part and improve it, use better components, so that the failure rate is divided by a factor p. So the failure rate is divided by 2, for example. P can be 2. So you improve the failure rate for this part, but not for this part. Well, if you do the math, you see that reliability improvement index will look very similar to the Amdahl's formula. It basically says the fraction that was not improved, and this is the fraction that was improved by a factor of p, dictates this reliability improvement index. In particular, if p is infinity, in other words, you make this part of the system infinitely more reliable. Of course, you can't do that in practice, but for the sake of argument, let's say p is infinity. Then the reliability improvement index, so this term basically becomes 0, will be 1 over f. If the fraction of the system that you left unchanged did not improve, as let's say 20%, F is 0.2, the maximum you can hope for reliability improvement index is 5. 1 divided by 0.2, no matter how much you improve this remaining part. It's very similar to Amdahl's law. That's why I call it analog of Amdahl's law for reliability. Very recently, a couple of months ago, I published another paper in IEEE Computer dealing with reliability inversion. So this is basically something, a concept that came to me as a result of a lot of decades, 5 decades working in dependable computing and reliability evaluation. So what is reliability inversion? If you look at the diagram on the left, a system has a particular reliability. That reliability is unknowable. There's no way to find the exact value of that reliability. The only surefire way of determining the reliability of an airplane is if you have millions of copies of that airplane and then you fly those for many, many years and just observe how many of them crash. But that's impractical. So there's a level of reliability that is unknowable. What we do through analytical models is establish lower bounds using some simplifying assumptions, some pessimistic assumptions about things that can go wrong. And we say, okay, the reliability of the system is no less than this. This is a lower bound for reliability. We don't know the exact reliability, but we know it's better than this with some high level of confidence, depending on what models we use. Okay, and if this distance is large, then we are basically losing here. We think the system is only this reliable, whereas it is much more reliable. And if you have two systems, one of them has a lower reliability, again, this is unknowable, but we can establish a bound, lower bound for it, that is closer to the actual value. Now look at these two systems. This is more reliable than this one in actuality. The bound that we obtained for this one is lower than this one. And therefore, if we were to judge which one of these two systems is better to use, we'll have to pick this one because the lower bound is larger. Remember, we don't know the actual reliabilities. All we know is that for this system, reliability is at least this much. For this system, the reliability is at least this much. We have the lower bound. Therefore, we have to say, okay, it's better to use this system, even though the first system is more reliable. This is what I call reliability inversion. The reliabilities are inverted due to these imperfections in our models that don't give us tight bounds for reliability, don't give us exact values. And here is basically reliability changes with time. So here I've shown system 1, its actual reliability, which is unknowable, and a model that we use to establish lower bound for it. This is system 2, its actual reliability, and the model we use. Okay, so in this example, we see that system 1 is more reliable up to this point in time. Then system 2 becomes more reliable after that point. Whereas the modeled reliability, the lower bound, is uniformly higher for system 2 compared with system 1. So again, we prefer system 2 because its guaranteed reliability is better than that of system 1. So this is an important distinction. So we want to develop models that are as accurate, as close to actual values as possible, but sometimes that's not an easy task to do. Okay, the second concept, so reliability I mentioned is the most important notion in today's lecture. Availability is probably the second most important notion. So what is availability? This is for repairable systems. So a system can have an operating state and a down state, but when it goes into the down state, we can repair it and bring it back up. The more quickly we do this, the faster the repair, the more time the system will end up spending in this up state. So let's say it's in the up state for 2 hours, then it fails, then 15 minutes later we bring it back up. So it's spent 2 hours here, 15 minutes here, and then a few more hours here. So the probability of the system being in the up state in the long run is its availability. So for example, if the availability is 95%, means that the system is in the up state 95% of the time in the long run. Okay, how do we compute availability? Well, availability is given by this equation, is 1 over t, availability for the system being available at time t is 1 over t, integral of the basically availability function, pointwise availability function, over the period 0 to t. Okay, in steady state, so initially, if the system is in the up state, let's say for 2 hours, for those 2 hours, availability is 100%. But then it fails, it goes into the down state, stays there, availability, which is the average time spent in this up state, declines, and then it can go up and down as the system moves back and forth between these two states. But in the long run, the system will spend some fraction of its time in the up state, and that's called the steady state availability. So the steady state availability is given by this formula, mean time to failure divided by mean time to failure plus mean time to repair. So repair doesn't usually take a constant amount of time because some failures are easier to fix, others take longer time. So to model this situation, we define a parameter, just as we have failure rate, lambda, we have something called the repair rate, mu. So for example, we say we have 10 to the minus 9 failures per hour. That's the failure rate, lambda. The repair rate, we can have 4 repairs per hour, meaning that repairs take on average 15 minutes. So this mu is generally a much larger number, 4 repairs per hour versus 10 to the minus 9 failures per hour. Therefore, this availability will be very close to 1 because mu is much larger than lambda, which is as it's supposed to be. You know, we hope that the availability is pretty close to 1. Okay, so mean time to failure divided by mean time to failure plus mean time to repair. The sum of mean time to failure and mean time to repair, sometimes called mean time between failures. And therefore, mean time to failure is 1 over lambda. Mean time to failure is 1 over lambda. Mean time to repair is 1 over mu. If you substitute and simplify, you get this. So that's availability, steady state availability. So this is the situation for such a system that has 2 states, up and down. So the system starts in the up state, it works for a while, then suddenly it crashes. It has just 2 states. If it's not up, then it's down. Then it stays down while we figure out how to repair it, how to fix it. Then it is fixed, goes back up, and so on. If I plot the availability of the system, availability is 1 for this period of time, then suddenly it starts declining, and it goes lower and lower as this time, more time elapses in the repair state, and then it starts going up again for this period of time, and so on. And if the expected number of failures are known and the repair, of course, is statistically distributed, in the long run, we have the steady state availability, which is the probability of being in the up state. The third measure, now these measures that I'm going to define are not as commonly used as reliability and availability. This one is known as performability. So what does this mean? This applies to systems that do not fail abruptly. They're sometimes called fail soft. So in this particular system, there are 2 up states and 1 down state. So the system starts here in up 2 state, and then perhaps something happens. Let's say it has 2 processors that are working, and one of those 2 processors fails, and the system goes into a degraded mode of operation with just 1 processor. And then sometimes later, that 1 processor may also fail, and the system goes into the down state. Or we may get lucky before that second failure occurs, finish repairing that first processor that had failed, and go back to this state. So this system can go back and forth between these 2 and not fail for a long period of time, and eventually it will fail, but then we can still repair it. Okay, so this system, let's say, has higher performance by a factor of 2 in this state compared with this state. So we define performability or average performance of this system as 2 times probability of being in this up 2 state plus 1 time the probability of being in this up 1 state. So here's a numerical example. Let's say the probability of being in the up 2 state is 0.92, probability of up 1 state is 0.06, and probability of being in the down state is 0.02. The performability of the system will be 1.90. 2 times 0.92 plus 1 times 0.06, 1.90, meaning on average the performance of this system is 1.90. Performance is 2 units in this state, it's 1 unit in this state, and 0 unit in this state. On average, it's pretty close to high performance. That's because the probability of being in this state is quite large, 0.92. Okay, we can also define a performability improvement factor similar to what we had for reliability improvement factor. So this is performability. What is the availability of the system? Okay, well, it depends on how we define availability. We can define, for example, the system is available whenever it is in either one of these 2 states. Although it has lower performance here, we may still consider it, we may still consider it available. And the steady state availability will be the probability of being in this state plus the probability of being in this state, which in this numerical example is 0.92 plus 0.06, which is 0.98. Okay, so this is basically variations in performance in such a fail-soft system. So the system starts in the up state, then it experiences some partial failure, goes into, in fact, there doesn't have to be just one intermediate state, it can be many other partially operational states. But let's say just take that one state, it goes into that state, partially up, it stays in that state, perhaps at some point it fails and goes into the down state. Then we repair it, bring it partially up, and then totally up, and so on. So performance fluctuates, and we define something called mean computation before failure. That's how much computation the system performs before it fails. In the case of availability, we said how much time the system spends before it goes down. Okay? Here, because we distinguish the behavior of the system in this high performance state versus low performance state, is the area of this under this curve that is important to us. How much computation does the system perform before it fails? That's called mean computation, on average, mean computation between failures. Okay, we then have the notions of integrity and safety. They're similar. Integrity is inward looking, meaning it's the capacity to protect system resources, for example, data. Safety is outward looking because we deal with consequences of incorrect actions to users. This will become clear as I'll show you the next few slides. A high integrity system we call robust because data is not corrupted by low severity causes. Something really must go wrong for data to be corrupted. So it has built-in capabilities for protecting the data so that if something goes wrong and it's not a severe problem, data is not corrupt. Data survives. Okay, safety is distinct from reliability because we can design a system to be fail-safe even though it's not very reliable. Fail-safe means simply it fails in a manner that is safe. So for example, it totally shuts down and it doesn't do anything and it suspects that something is wrong in order to avoid doing wrong things and causing further damage. So we'll talk about fail-safe systems towards the end of the course. It's one of the last topics that we cover. So we can make a system fail-safe, for example, if human lives can be in danger, because a system that fails safely, and we know that it has failed and it's in a particular state that we can detect, then of course we won't rely on that system and therefore we won't endanger any human lives. So for example, if the flight control computer is a fail-safe system, and when it fails, the pilot knows immediately that it has failed, and it no longer controls anything in the aircraft, then the pilot can take over, do manual procedures, and land the plane safely. So this particular computer may not be reliable because it actually fails quite often, but it fails in a safe mode. Okay, that's the distinction. So a fail-safe system may not be actually very reliable. They're two different things. Okay, so for safety assessment, in order to quantify safety the way we did for reliability, availability, and performability, we need some basic definitions. So we have a system, let's say it has an up state, where the system is working perfectly well, and it has a bunch of down states, one or more of which are safe down states. In this case, I have shown just one safe and there are multiple unsafe, one or more unsafe down states. So the system as it's operating, it can fail. If it fails in a safe mode, it goes into this state. If it fails in an unsafe mode, it goes into one of these unsafe states. Okay, so this safe down state is actually a desirable state. If the system is going to fail, would rather it fail in this state. So from the point of view of safety, the safe down state is really as good as the up state because there are no safety issues in either case. Whereas the unsafe down states, there's unsafety, there are consequences. Okay, now the reason I distinguish multiple unsafe down states is that the consequences of the system going into different unsafe states can be different. And the consequence is basically what happens, the penalty that we have to pay, either financial penalty when the system fails and we have to uh, pay money to compensate for damages, whether the damage is to life or to property and so on. So there may be different consequences, different costs associated. So basically, the total cost, safety cost of the system will be the probability of being in this state times the cost consequence of being in that state, plus the probability of being in this state times the cost or consequence, and so on. That's why it's helpful to have these multiple states because consequences may be different. Okay, now let's say we have just one unsafe down state. Then risk assessment, of course, risk assessment is a big discipline. There are courses offered, safety engineering. So I'm going to present a very simplified view of risk assessment. So the risk of something is the product of two factors: the frequency of that thing happening. The frequency is sort of like probability, times the magnitude of the consequence. So how many events per unit time are we expecting? And what is the consequence, financially or otherwise, of each of these events? So risk is the product of probability and a severity. Okay, so if something happens with probability 1%, 0.01, and the consequence is that we lose $1,000, the risk will be the product of 0.01 and 1,000, which is $10. So if I can lose $1,000 with probability 0.01, 1%, the risk to me is $10. I'm risking $10. And given that human beings are risk averse, this is one of the interesting observations about human being studied in psychology. We are risk averse, and if there is even a small probability that we lose $1,000, we usually do not view it as, okay, on average, I'm going to lose only $10. It's not a big deal. I get worried about that small possibilities of losing $1,000. And this is basically where insurance companies operate. An insurance company comes to me and say, okay, you're worried about this losing $1,000 with 0.01 probability. I'm going to insure you against that loss if you pay me $30. So you pay an insurance premium of $30, and then you will never lose that $1,000. Although the average loss was $10, and you're actually paying more in insurance premium than that average loss, you're still satisfied and comfortable that your maximum loss is that $30 that you paid, Okay, and by paying that $30, those $30, you avoided the possibility, small as it might be, of losing $1,000. Okay, so this is a very simple view of risk. It's a product of a probability and severity. The magnitude of severity is often measured in some suitable units, say dollars. And this is one of the, I don't know, regrettable things that we do in safety engineering. If the risk is to human lives, and we have to quantify that risk, we have to assign a dollar value. So for example, when a plane crashes, we have some financial losses, plane itself crashing and so on, and there are also loss of life. In order to sort of evaluate the total risk, we know the cost of the plane, so that's the direct dollar loss. But we also lose some people, and we have to assign dollar values to those lives in order to be able to compare losses. Of course, some people say, oh, you can't put any value on human lives, but that's really not a reasonable thing to say. You can't say human life costs infinite dollars, because then you can't fly any airplane. Because if human life is worth an infinite number of dollars, then even a tiny risk of plane crash basically paralyzes you and you won't fly on any plane. So in practice, we actually do assign those dollar values to human life. Okay, so here is safety assessment with more transitions. So here I have an up state, and I have a safe down state. The system goes there and stays there. It's safe. If it goes to an unsafe state, I may try to repair it and take it back to the up state, or maybe push it into the safe state. Sometimes when the system goes into the safe down state, something happens and it actually transitions into an unsafe state from there. We have to watch out for these transitions. So we can make this model as complex as we care to in order to more accurately model the system. Okay, this slide I'm going to let you read on your own. Fallacies of risk. I'll just mention item 1 on the slide. So one of the fallacies of risk is the fallacy of sheer size. If the risk X is accepted and Y is a smaller risk than X, then Y should be accepted also. This makes sense logically. If I accept risk X and there's another risk Y that is smaller, then I see no reason why I shouldn't accept that smaller risk. However, consider this example. Let's say X is the risk of driving a car. Y is the risk of flying on a plane. And for the same distance traveled, flying on a plane is much less risky. It entails much lower risk than driving a car. If you want to go 1,000 miles, going on a plane is much, much less risky in terms of, the possibility of dying than driving a car for 1,000 miles. Yet many people, accept the risk of driving a car, whereas they're just too scared to fly, even though they know, there's data to suggest that risk of flying is much less than risk of driving a car. So there are some psychological factors that are at play here that make that logical conclusion not valid. So one of the psychological factors is familiarity. If you have, you know, driven a car since you were a young person, so you have driven a car for many, many years, you're familiar with driving a car, you have done it on a daily basis, so you don't think much about the risks. Whereas flying is something that you do occasionally, so you do worry about the risk. So these 10 fallacies are very interesting. And if you find them interesting, you can refer to the original reference cited on this slide to get more detail about these fallacies. The final topic that I'll discuss today uh, relates to privacy and security. Privacy is compromised when confidential or personal data are disclosed to unauthorized parties. Security is breached when account information, for example, in a bank, is improperly modified. Someone goes and modifies your account balance, for example, reduces it. Their security has been compromised. Privacy is when the person goes into the bank's computer and grabs your account number, uh, various information about you, the social security number, and so on. Of course, both of these are important, but they're different concepts. Now, security is distinct from both reliability and safety. A system that automatically locks up when a security breach is suspected may not be very reliable or safe, but it's secure. So if the system detects the possibility of a security compromise and it just shuts down, doesn't allow access to anybody, it will be secure. But it will not be reliable because it's not working when it's locked up, and it may not even be safe because that lockup state may not be a safe state. So these are distinct concepts. Now, how do you model privacy and security? Well, for security, it has been suggested that we should model it just like risk. You know, security breaches have some frequency, some probability, and some consequence. Okay, so if you multiply the probability by the consequence, again, quantified in some way in terms of dollars, but theoretically you should be able to do this. There's just one problem. Whereas for safety, the events that cause a lack of safety are really probabilistic, and you can assign probabilities to them. Things like hacking, intrusion into systems are not really probabilistic events. You know, somebody is sitting there looking for an opportunity to infiltrate a system. It doesn't just do randomly, probabilistically. Now, if you consider many, many systems, you know, millions of systems across the world, then you can say that there's some probability involved. You know, a certain number of these will be hacked, will be compromised. So in that sense, you can assign probabilities to large numbers of systems. But for any given systems, for example, in your computer, you're trying to do security assessment, you really cannot assign a probability that your computer will be hacked and therefore there will be a security breach. So this is still work in progress. In other words, we still don't quite know how to quantify security. So the simple idea to treat it like uh, safety, risk, uh, really doesn't work. Okay, so let me stop at this point. That's the end of chapter 2. Chapters 3 and 4 also will have individual lecture, one lecture per chapter. And then after that, I will start, as I mentioned in the first lecture, combining 2 chapters into 1 lecture in order to have an opportunity to finish the entire textbook by the end of the quarter. Bye for now. Stay safe and see you in lecture 3 or during one of my office hours.